when you want. Thank you.
Sorry, I didn't hear you.
You can go ahead. Thank you.
All right, welcome everyone to the 16th seminar. Today we have Celsa tell us about her PhD work that we've been working on in the past couple of years. We'll hear more about this next week, actually, during the Pegasus event. So Celsa joined the Institute of Space Sciences about 2 years ago, first as a machine learning engineer, and then as a PhD student in the summer of 2022. Celsa has a background in mathematics, but has always had a strong interest in astrophysics and decided that she wants to do a PhD in that field. She's also worked in industry for a while and has got quite a big background in coding and machine learning methods. So she was the perfect person to sort of tackle this problem that we've been working on for a couple of years, and she will present some of our recent results on isolated pulsar population synthesis with simulation-based inference.
Okay, so thanks, Vanessa. Hello, everyone. As Vanessa said, I'm going to present our work in isolated pulsar population synthesis with machine learning with simulation-based inference that we also do with Michele Ronquidas, also is a PhD here. So in this talk, I'm gonna give first a brief introduction, then I'm gonna explain a little bit what pulsar population synthesis is and what is our population synthesis made of. Then I'm gonna explain simulation-based inference, and for that I need to explain a little bit the basic concept of machine learning. And then I'm gonna jump into the inference results and finish with a brief outlook. So let me start with introduction. Just for you to remind what a neutron star is. Neutron stars are born in core collapse supernovae of a star of around 10 to 25 solar masses. Usually they are characterized by distinct properties such as the high compactness. So they are neutron stars that they are a radius of 10 kilometers that encloses masses of around 1 and 2 solar masses. They are also characterized by the fast spin. They spin really fast, and also they have strong magnetic fields around 10 to the 9 and 10 to the 15 Gauss. They are also characterized by their, when they emit in radio, they have this lighthouse effect due to the misalignment between the rotational axis and the magnetic axis. So then, as it is sketched here in this GIF, you are going to see a neutron star when this beam crosses your line of sight. And due to this lighthouse effect, we can measure also the period of the neutron stars, and we can measure also the period derivative. That's why we usually represent the galactic neutron stars in our galaxy in this diagram that is called Pipidot diagram. I'm going to mention throughout the talk a lot about Pipidot diagrams, so just for you to remember. And the Pipidot diagram is the diagram where we have in the x-axis the spin period and in the y-axis the spin period derivative. And as you can see, we have that different classes of neutron stars are in different places of the Pipidot diagram. If you now look at the top right, we have magnetars in green. We have that magnetars are neutron stars that are characterized by the high magnetic field, and also they emit bursts and flares in X-ray. If now we look at the bottom left of the diagram, we have the pulsing binaries that usually we think that they are all neutron stars that underwent a process of recycling due to the accretion from the companion. So that's why we have that, since they are recycled, they have the process of spinning up. So they are at the left of the diagram because the periods are shorter. But in this work, we are going to focus in the ones that are isolated radio pulsars, that are this the bulk of the pulsars in gray. And they usually, we think that they are powered by the rotational energy. The luminosity is powered by the rotational energy, and typically they emit in radio. Let's now enter in the explaining what a pulsar population synthesis is and our population synthesis specifically. We can roughly estimate how many numbers of neutron stars we have in our galaxy. Let's say that we assume that there are 2 core collapse supernova per century. Then we will multiply this by the age of the galaxy, and then we can approximate how many neutron stars we have. And we think that there are around 10 to the 8 neutron stars in our galaxy. But we just detect 3,000 of them due to, first, to this geometrical effect that I just told you, that since the emission is pink, we lose a lot of pulsars because they don't cross our line of sight, and also because, of course, of observational biases. So how can we study really the whole population of neutron stars if we just see such a small fraction of them? We can study through this pulsar population synthesis. That population synthesis is summarized here. So first, in the population synthesis, we start modeling some birth properties of the neutron star via Monte Carlo approach. Then we evolve some properties in time. And since we want to compare our simulated neutron star population with the observed population, we need to apply this, we need to mimic these observational biases to then compare with the simulated, with the observed data. The goals of this work mainly are constraining some natal properties for the neutron stars, and also you can see here in this work, they estimate the neutron star birth rate for different classes. And as you can see here, the numbers are different, and also if you look at the cumulative birth rate of the neutron stars in our galaxy, is summed up to around 10, but is much larger than the one that we have for the Corpora supernova. That is not consistent. So what we think maybe is that instead of being these different classes are different classes, maybe there is an evolutionary link between them. So with the neutron star population synthesis, we can also study this evolutionary link, and also we can estimate it better. So let me start to explain the key ingredients of our population synthesis that are summarized here in this graph. We add the dynamical evolution, so how the neutron stars move around the galaxy. We also have the magneto-rotational evolution, that is the evolution of the period, the magnetic field, and the key angle, which is the misalignment angle between the rotational axis and the magnetic axis. And also, of course, we need to add the observational biases, and to do so, we need to add we need to model the luminosity in radio. And then, as the final step, is going to compare our simulated data with observed data to tune some model parameters. So let's start with the dynamical evolution. We think that neutron stars are born in star-forming regions, typically in the spiral lines, and also because of the supernova, they receive kicks. And in order to do the dynamical evolution, we need to do some assumptions in our population. We first assume that the initial positions are sampled according to the galactic electron density distribution. That is in this plot here, the galactic electron density distribution. We assume that how the neutron stars distribute in the Z axis, let's say in the galaxy, the height of the neutron stars follows an exponential this model. We also assume that the key velocity follows a single component Maxwell, and also, of course, to perform the dynamical evolution, we need to assume a galactic potential for our galaxy. Once we have assumed all of this, then, is it there? No, sorry. Okay, no. To do the dynamical evolution, basically what we can do, why is not playing? But it was working before. So to do the dynamical evolution, basically what we have to do is just solving the Newtonian equation of motions for the neutron stars. And you can see here a video in the top left, in the left is the top view, and in the right is the side view of the neutron stars evolving in our galaxy, for our simulated galaxy, of course, and different colors represent different ages. Once we do the dynamical evolution is totally decoupled from the magneto-rotational evolution, so we can perform the magneto-rotational evolution. Again, is the evolution of the magnetic field, the period, and the misalignment angle. We think that the magnetosphere of the neutron star itself is a torque onto the neutron star. This makes the neutron star to spin down, so to get to have larger periods. And also this angle here, that is the misalignment angle, that is the angle between the rotational axis and the magnetic axis, tend to align with time. In order to make our code more realistic, what we add is also the magnetic field decay due to the Hall effect and the omni dissipation in the crust. And we add it by adding the curves from the 2D magnetothermal code of Vigan 2021. And we also need to do some assumptions in our magneto-rotational evolution. We need to assume which are the distribution for the initial period and the initial magnetic field. For the initial period and the initial magnetic field, we assume log normals. And for the magnetic field decay at late time, so for times greater than 10 to the 6, we assume that the magnetic field decay is following a power law. And in our population synthesis in general, there are a lot of free parameters, but in this precise work, we are gonna fix all of the parameters, and the ones that we are gonna let them free are these 5 here, are the 2 for the initial period distribution, that are the mu and the sigma for the log normal. Then there are the mean and the sigma also for the initial magnetic field. And then we also are gonna let free this LA parameter, which is the power law index for the magnetic field decay at that time. So we are gonna have 5 free parameters in our model. The magneto-rotational evolution is basically solving these differential equations here that are the coupled differential equation for the period and the misalignment angle. And you can see here how the stars move in the pipidal diagram for our simulator, where different color represents different initial magnetic fields. Stars start at the top left of the diagram, then follows the constant magnetic field lines that are depicted here. You can see here the constant magnetic field lines. And then once the magnetic field decay, the trajectory bends, and then they start to move vertically in the pipidal diagram. So the stars start at the top left and then move to the right because the period is increasing during time, because the star spins out. And since we want to compare with the observed data, we need to take into account the observational biases. And to do so, we need to model the radio emission. To model the radio emission, we assume that the luminosity in radio for the neutron stars is proportional to the loss of the rotational energy. And then in our simulation, we remove those pulsars that doesn't point towards us. So basically that this beam in radio doesn't cross our line of sight, which are around 90% of the pulsars. And then for the rest, we calculate the fluxes of each of the pulsars. We can calculate the fluxes because we assume an intrinsic luminosity for the pulsars. And also we calculate the geometry of the beam. So we are going to have the solid angle. And then we have the distance because we did perform already the dynamical evolution. So once we calculate the fluxes of each of the neutron stars, then we can count as a pulsar if it's detected for a given survey, if it exceeds the sensitivity threshold for each of the surveys. And I show you here the 3 surveys that we add in our population synthesis, that are all of them are done with the Parkes Radio Telescope, that is a telescope in Australia. The first one is Parkes Multi-Beam Pulsar Survey. I show you here at the top right a plot of galactic longitude in the X and galactic latitude in the Y, and PMPS, which is the Parkes Multi-Beam Pulsar Survey, are the yellow dots. And you can see that this survey is mainly focusing the galactic disk and has detected around 1,000 isolated pulsars. Then we also add the high time resolution universe survey, which is a survey also that is more or less centered at is in orange here, the orange dot. It's also centered at the galactic disk with a little bit higher latitudes in sky coverage than PMPS. And also the resolution was higher than compared to the Parkes Multi-Beam Pulsar survey. And also detect more or less around 1,000 isolated pulsars. And the last survey that we had is the Swinburne Parkes Multi-Beam Pulsar survey. This survey is focused more out of the galactic disk, so higher latitudes are the blue dots in this plot here. And as you can, and since they are higher latitudes, this means that it's gonna be able to detect other pulsars because are the pulsars that has time to escape the galactic disk. And this survey more or less detect 200 pulsars. So once we have all of our pulsar population synthesis set up, can we really constrain some physical properties of the whole neutron star population synthesis if we just see such a small fraction of neutron stars? This is the mainly question that we want to answer in this work. And we are gonna focus just in these 5 properties. As a reminder again, there are the 2 for the initial period distribution, 2 for the initial magnetic field, and then this parameter for the magnetic field decay at no time. So now when this is when machine learning comes in, we are going to try to do the statistical inference using simulation-based inference. And to do simulation-based inference, I need to explain a little bit what some basic concepts of machine learning. Maybe all of you already know, but just a brief reminder. Neural networks are algorithms that are spanning human brains, and usually they are used to solve classification and regression problems. So this is a sketch of a neural network. So a neural network, you can think of a neural network as the composition of different layers, where in different layers there are different neurons. And in this neuron is the composition of a linear function with a nonlinear function. And in this linear function, we have some free parameters that are called the weights, that are this W1, W2, that are the free parameters of the algorithm. And then let's say as a toy example that we will have this problem, that we have images of cats and dogs, and we want to classify them. So since neural networks are supervised learning algorithms, we need to train them. So we need to provide training data that are the one for the toy example is this one here, that is images of a cat and dog that are already labeled. So what we do in the training is we pass the training data to the neural network. And then the neural network is, what we do in the training is we are going to try to find the weights, this W1, W2, that minimize the error, where the error is the distance between the predicted level and the real level. So we want this distance to be as close, we want these two levels to be as close as possible. And we are going to do this by a process that is gradient descent, basically. So once the neural network is trained, we are going to have that each of the weights, we are going to have a value for each of the weights. And then we are going to hope that if we pass to the neural network an image of a cat, then the neural network is going to be able to say, okay, this is a cat. In this work, we use a specific type of neural networks that are called convolutional neural networks that are mainly used for structured data, to process structured data, such images. And these convolutional neural networks are made of two filters. The convolutional filter, which is the one that is in charge of extracting the main feature of the images. And then there is the pooling filter, which is the one that extracts the most relevant features and then speed with this process, speed up the training. And since I was explaining all of this of the machine learning setup, because we use simulation-based inference for doing our statistical inference, because we want to infer some parameters, but we don't want to just have point estimates for these parameters. We want to have also an uncertainty related to these parameters, so having a credibility interval. And for this, we are going to use the Bayes theorem. The Bayes theorem is telling you that the posterior distribution, which is the probability of the parameters given the data, is going to be equal to your prior knowledge on your parameters times the likelihood of the model, which is the probability of your data given the parameters, over the evidence, which is the probability of your data. But for for complex simulators as ours, this likelihood here is usually implicitly defined in the simulator and is often intractable. So how can we solve this problem? We can solve it by using simulation-based inference, which is a likelihood-free inference model, meaning that you don't need to define an explicit likelihood to solve, to approximate the posterior distribution of your data. I'm going to briefly summarize the main approach of simulation-based inference, but we are going to just use one of them. The first one is the neural posterior estimation, which uses a neural network to approximate directly the posterior distribution of your data, of the parameters, sorry. But the advantages of this method is that you don't need, after training, IMCNC for extracting the samples from the final posterior. But once you train, you cannot change the prior distribution that you chose at the beginning. There is also another method that is called neural likelihood estimation, where your neural network emulates the simulator itself, and then you are going to have a direct access to an approximation of your likelihood. The advantage of this method is that you are going to be able to change the prior after training, but you are going to need an MCMC-like method to sample from the final posterior. And the last method is called neural ratio estimation, where your neural network learns the likelihood to evidence ratio. And again, you are going to need MCNC to sample from the final posterior, but it's true that you can change the prior after training. We are going to focus mainly, we're going to just using this we use in this work already. Just one of these approaches that is called the neural posterior estimation. How this neural posterior estimation works? First, you need to assume a prior distribution. In this case, we assume a uniform prior distribution for all the parameters. So we sample from the prior distribution the parameters, which is again, as a reminder, there are these 5 parameters: 2 for the initial period, 2 for the initial magnetic field, and 1 for the magnetic field decay and daytime. Then when we sample the parameters, we give this parameter to our pulsar population synthesis code. And then for each of the parameters, we are going to have a simulated neutron star population for given the parameters. Then how we will represent this simulated neutron star population as a PP dots, where we are going to have 3 PP dots because we model 3 surveys. So we are going to have 1 PP dot per survey. And as I said before, neural networks are supervised learning algorithms. And this is how basically in this diagram here, this is how we generate our training data set. That is going to consist in tuples of the 3 PP dots times the parameter that we use to generate these PP dots. So we are going to give the training data to the neural network, train the neural network, and we are going to hope that the neural network is going to learn the approximate posterior distribution of the parameters. This neural network is called conditional density estimator. That is, in our case, is the combination of a convolutional neural network that takes the 3 PP dot diagrams, and then as output is going to extract the main feature of these PP dot diagrams, and as output is going to save into the main features into a Laplace vector, into a flat vector. And this vector is going to be the input of a mixture density network that is a fully connected neural network that has that the output is going to be the Gaussian mixture parameters, because we are going to approximate our posterior distribution by assuming that it's a mixture of Gaussians. So basically what we are going to have is that when we are going to train this neural network with the PP dot and also the label, which are going to be the parameters that we use to simulate this PP dot. And once this neural network is trained, what we can do is, since this is called amortized posterior, but this type of neural networks approximate, because it is called amortized because given any observation or simulated data, the neural network is going to be able to give you the posterior distribution for this simulated or the real observed data in seconds. And I summarize here the advantages and the disadvantages of the MP approach. The advantages mainly is that you don't need to use or define an analytical likelihood for your data. And also you don't need to assume in some cases that people, when they doesn't have the likelihood, assume a measure of similarity between the simulated data and the observed data. We don't need also to assume a measure of similarity. The main also advantage is that after training, the inference process is just takes seconds to do an inference process. And also due to this amortized nature, we can test the quality of our neural network, of our approximate posterior distribution. The disadvantages mainly are that you need a large data set in this case to train the neural network. And also, of course, your approximated posterior is going to be as good as your simulated. And I summarize here 3 applications that because people in astrophysics is already using SBI a lot. And I summarize here just 3 of applications in different fields. The first one is they use SBI to infer, the sum of the masses of the Milky Way and the Andromeda galaxy using lambda CDM simulation with Gaia data and Hubble data. There also another the typical also approach, the typical papers where you see SBI is in gravitational wave papers, where they use SBI to infer the physical parameters of the detected gravitational wave to use it in real-time data analysis. And also there is another paper where they use SBI for retrieving the physical parameters from the spectroscopy of exoplanets to retrieve the physical parameter for their atmospheres. And I'm going to jump now into our infer results. I show you here the training and the validation curve, and we train in 360,000 simulations in total. we use 90% for training and 10 for training and validation, sorry, and then we use 10% for testing. These are the validation and the training curve, and as you can see, the neural network is able to also generalize in the validation curve, because there is almost no overfitting. But in this case in this type of neural networks, the loss function is not really giving you a lot of information, because you are not predicting just one number or one point estimate. We are predicting the posterior distribution. So what people usually do to check the quality of your approximated posterior is doing the posterior predictive set. That is basically, you can sample a parameter from your prior distribution, then you can simulate, using your simulator, you simulate the neutron star population for this parameter, and then you give this to the neural network. And the neural network is going to give you what is the posterior approximation for this simulated neutron star population. Since it's simulated data, you know the ground truth. So the parameter that you use to simulate this neutron star population, so you can compare. And in blue, I show you here the ground truth, so the parameter that we use to simulate this data. And in purple, I show you here the median for the 1D marginalized posterior, for the approximate posterior distribution. And as you can see here, both points are really close together, meaning that the neural network is able to approximate, in this case, the posterior distribution. But of course, also the neural network itself has some hyperparameters. So we didn't have enough computational resources here in this work to do cross validation. But we did different experiments where we vary different hyperparameters. For example, you can vary the learning rate, you can vary the batch size, you can vary the resolution of the image. So we train 22 different neural networks that are, we call them experiments, each of the trained neural networks, with the same training dataset, but each of the neural networks have some difference in the hyperparameters. And now, since this amortized nature of each of the neural networks, we can give to the neural network the same test sample. And each of the neural networks is going to give their approximation for the posterior distribution. And I showed you here at the bottom one sample for a test sample from our test dataset. So a sample that the neural network wasn't trained on. And you can see that the white curves are the approximated posterior distribution for each of the trained neural networks. And in blue, the ground truth. You can see that the neural networks more or less agree between each other. And also that the ground truth is enclosing the support of the approximated posterior distribution, meaning that the neural network is able to learn the approximated posterior distribution of the parameters. But also what you can do is instead of just taking one of the neural networks, you can combine all of them together into a posterior that is called ensemble of posterior that I show you here in yellow. And in this case, we didn't use the 22 different trained neural networks because we saw overfitting and the training wasn't well behaving one of them. So we removed these 3, and then we do the sample for the 19 experiments. These checks are just taking one test sample, but we also want to check how the neural network is performing in the whole test dataset. So the data that the neural network wasn't trained on it. So what we can do is the coverage probability plot, and we expect that for a well-calibrated approximated posterior distribution, you are going to have that this plot, it looks like the diagonal. What this coverage probability is measuring the fraction of the test samples for which the ground truth falls within the corresponding 1 minus alpha credibility region. This what means, as an example, if we take 0.8 credibility level, this for a well-calibrated neural network, this is going to tell you that the coverage probability is equal to 0.8. This means that for the 80% of the test samples in your test dataset, this is going to happen. So the ground truth is going to fall within the 0.8 credibility interval. But if you don't have that, the coverage probability look diagonal, it look like the coverage probability lies above the diagonal, then this means that the approximated posterior distribution is conservative, so it's wider than your ground truth. But in the other case, in the other hand, if you have that the coverage probability lies below the diagonal, then this will mean that your approximated posterior distribution is overconfident, so it's narrower than the ground truth. And here I show you the result for our work. In white, there is the coverage probability for each of the experiments, and as you can see, they are close to the diagonal, meaning that our approximated posterior is well calibrated. And in blue, I show you the ensemble coverage probability, and it gives a conservative approximated posterior. That is something that you expect when you do ensemble method, when you combine different neural networks. Now that we could check that our neural network is well calibrated, and we can assess the quality of our approximated posterior distribution, we can use the neural network to approximate the parameters, the posterior distribution in the observed population. That this was the main goal of this work. So we give to the neural network the observed pivot diagram, and then ICE-CSIC is going to give you the posterior distribution for the observed population. Here is the correct proof, but for simplicity, I'm going to show you just here the 1D marginalized posterior distribution for each of the parameters. In white, there is the different approximated posterior distribution for each of the experiments, so for each of the trained neural networks. And at the top, you have the median and the 95% confidence interval for the ensemble posterior, that is in yellow. So as you can see, the neural network is able to really approximate, and the posterior distribution is really narrow for the magnetic field, meaning that it seems that the neural network is able to learn the posterior distribution for the magnetic field. But in the case of the period, you see that the posterior distribution is a little bit wider. This is because the information for the initial period is lost during the magneto-rotational evolution. So also in previous work, they saw that that is much more difficult to infer the parameter for the initial period than for the magnetic field. And in this case of this parameter that we use to model the magnetic field decay at late times, you see that for different neural networks, you can see one here and also the other one here, that the posterior distribution support doesn't overlap between different neural networks. At the beginning, we thought that this could be a problem of the training of the neural networks, but then we didn't see any of this behavior in any of the test samples. And also the coverage probability plot was looking that good, that was a well-calibrated approximated posterior. We just see this for the self data. So what this is telling us is that our prescription for the L8, for the magnetic field evolution late time, should be revised. Not and the neural network was like the training, wasn't any problem with the training. It was a problem with the simulator. We also compare our work with previous work. And in the left, I showed you the initial magnetic field distribution, and at the right, initial period distribution. You can see at the left that our work gives estimates a little bit larger than previous work. This could be due to the fact that we add a more realistic precision for the magnetic field evolution, and also that we add the couple evolution for the P and the Q angle. And in the case of the period, we couldn't compare with the Guyon or CSLAS because they use a normal distribution to model the initial period distribution. But we could compare with Clocher that use also a log normal for the initial period. And as you can see, the median of the mean value of both works agree. Although it's true that our work is a little bit narrower, the posterior, the period than from Clocher. We code our simulator in a way that we could also constrain the birth rate of the neutron stars in our galaxy. Here I show you the birth rate for each of the surveys. We see that these estimates are a little bit smaller compared to those of previous work, but it's true that they are estimates that are really close to the recent Corpora supernova estimates. And as a takeaway messages, I hope that I convince you that with pulsar population synthesis, we could study the whole neutron star population, just seeing such a small fraction of neutron stars. And with this, we can also constrain the birth properties and also some physical properties of the neutron stars. And I hope that I convince you also, although a little bit more difficult, that simulation-based inference has opened up the possibility of doing statistical inference without the need of and relying in a simplified likelihood when you have a complex simulator. And in future work, we want to improve our simulator by exploring different assumptions for the initial period and the initial magnetic field. we also want to add different wavelengths, like the gamma ray and the X-ray emission. And in the case of the simulation-based inference, we want to do a active learning approach where instead of giving to the neural network a training data set that is focusing the whole parameter space, what you do is that the neural network is going to be focused just in the parameter space, in the place of the parameter space that is closer to your observed data. And this is going to reduce the number of simulations that you need to train. So then we are going to be able to also infer more than 5 parameters. And if you like this work, you can check out the paper for more details. And with this, thank you.
Right, thanks very much. Are there any questions in the room?
Maybe it's a very main question, I don't know. Is there a way to predict a distribution of the different angles of the beam, let's say, in a galaxy, as far as in a galaxy? I mean, does it depend on any physical conditions, or it's something totally random?
I think it's random. Or you can predict. There is a physical meaning for the misalignment angles or for the angle between the rotational axis and the magnetic axis. But in how it's aligned the neutron star compared to us, let's say, this is random. It's true that as wider is the aperture of the beam, so as wider is the beam, you have more probability to detect the beam because it's wider the beam.
Yeah, so I guess if we could have this information, then I guess we could probably ask him this distribution or whatever, and then you wouldn't need to consider to assume a 10%. You know,
no, we didn't assume it. We assume a random angle for how the beam is how is the beam inclined with respect to us. This is randomly, and then we remove those that doesn't point towards us. But okay. It's not something that this 90% is an approximate because it depends also in the parameters that you put in at the beginning. So it really changes between one simulation and another one. Okay. But it's a huge fraction. I was saying 90% because it's a huge fraction of them.
And so are you sure that this incompleteness in the observed sampling, it's only because of the...
No, there are also observational biases, of course. Yeah. Like, for example, the DM, as far as I know, the neutron stars that are close to the galactic center, the pulse of that you see, it gets dispersed because of the electron density that is in between you and the source. So if this person is really large, then you can miss the pulse because you don't see the pulse, it's a dispersed pulse. So also you have this, and also the luminosity because the sensitivity of your...
But I mean, it's not something that you want to quantify.
We quantify it in here.
Yeah. But I mean that so you know exactly the percentage of the needs only because of the limit.
Yeah, we could quantify, but it's true that it depends in the initial period and everything, because also it depends on how wider is the pulse. So yeah.
Thank you.
When you showed the distribution of the parameter AB, the one that didn't match.
The late parameter. I don't know why it's this one.
How did you define it in your model? So how do you put
it?
Yeah.
I have a backup slide actually.
Yes, is A late or what is it?
A late.
Yeah.
Okay. So we have that we model the magnetic field evolution with the 2D magnetothermal code of big and all, but from 10 to the 6 years on, the equations more or less are not reliable for cold and all neutron stars. So what we do is we model the late time decay as a power law, and this late was the power law index.
But then you think that the fact that we couldn't find good distribution due to this approximation, because the model has learned something.
Yeah.
But then the observations may be
Well, it's true that we don't have much stars here because they are really old. And also we think that maybe it could be also because we fix other parameters that you can vary. So maybe this is introducing some biases. And you can see the biases just in the E8. And
Because
or
it-
maybe, yeah.
Because this is the only parameter that has all this uncertainty in here.
Yeah, the period a little bit. You can see the period also a little bit,
Okay.
but not that much. Yeah, and also, as far as I understood, but this is magnetic field stuff, so I'm a mathematician, so it's difficult for me. But as far as I understood, you also can have different cores for each of the stars because you can change the envelope. The envelope can be different for each star, so maybe there is not just one prescription for all of the neutron stars. Maybe we need something more flexible.
All right, are there any questions online? Please unmute yourselves and type it in the chat.
Exacto, pero I don't know. Message. Yeah.
All right, any final questions in the room? Okay, if not, then let's thank Celsa again.